Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. We will study the topic bipolar junction transistor as described in the syllabus of Abdul Kalam Technical University, Lucknow, under the subject of fundamentals of electronics engineering. So this is one important topic. Also, it can be said as a complex topic which is not very difficult to understand, but we will go gradually to understand the topic very well. So here there are some pictures for the transistors, the bipolar junction transistors. So the technology, the semiconductor devices and all these are vastly made by the transistors, as we all know. So here are some pictures shown in the diagram for the transistor. Basically, two types of transistors are available. First is PNP transistor and second one is NPN transistor. So what is PNP and NPN? So NPN is made up of two diodes. First will be the N and P, first diode, and then the second diode PN. So P will be the common to both the N regions. So this is a NPN transistor, and PNP, the N will be common to both the P type of semiconductor. So here the PNP and NPN are the two types of transistor, as we all know, and the terminals can be, there are three terminals in any transistor, that is emitter, second one is base, and third one is the collector. So here the PNP transistor, how to make it, just so this is P, N and P. So here one thing we can notice, this particular terminal, this is P type, this is N type, and this is again P type. So we have two junctions, first junction here and second junction in this. This is the emitter terminal and this is the collector terminal, and this will be the base terminal. If I talk of NPN, the same will be the configuration and the junction which we can take. So here this is N, P, N. Noticeable point is, out of these two ends, the emitter width is higher than this N region. So this is less, and this P width is lesser than both the N regions. So this width is lesser than both, and this is again emitter terminal, this is again collector terminal, and this is again the base terminal. Okay, so here the terminals can be labeled as emitter, base and collector. So the NPN BJT consists of three semiconductor regions: the emitter region N type, the base region P type, and the collector region N type. Similarly, the PNP BJT consists of three semiconductor regions: the emitter region, the base region, and the collector region. In PNP, the base will be the N type. So if I talk of in terms of symbol, see for symbol, this is the symbol for the transistor. So let's say I am making the PNP, PN and P, right? So this is my base, this is my collector, and this is my emitter. So since current flow from positive to negative, so if I put the arrow from P to N type, so this is my symbol for PNP transistor, right? Okay. Similarly, if I talk of NPN, let's say N, P, N, emitter, collector and base. Okay, again I will flow the current from positive to negative terminal, and I will put arrow like this, and this will be the symbol for NPN transistor, right? So here we can have the symbol for PNP and we can have the symbol for NPN, right? So this is the simple introduction for the NPN and PNP transistor. This is the, as I said, the arrow is inside, the transistor is PNP. The arrow is outside, the transistor is NPN. Okay. So this is the symbol for the PNP and NPN transistor. Now coming to the biasing part. Okay. And let us see how the biasing has been done. This is my emitter and this is my base. Let's say take PNP. Okay. So P type, N type and P type. P type is positive. If I connect this terminal, battery terminal, to positive terminal of battery to my PNP, then it is forward bias. And if this is my P type and I have connected my negative terminal to the collector, then it is the reverse bias, right? Forward bias and reverse bias, right? Similarly, if I want to connect my NPN transistor, the emitter and base with this VEE battery, and I have connected the N type emitter to negative terminal, then it is again forward bias, and this N type has been connected to the positive terminal, so this is again reverse bias. So understand the first terminal has been forward bias, reverse bias in both the configuration as shown in the diagram, but we can have all the arrangements too, like I can connect my E, B and BC, both the junction. Here forward reverse has been shown, okay, and we can connect as forward, we can connect as reverse, and we can also connect as reverse forward, right? So there may be 4 types of connection possibilities while we are biasing our transistor. So that point we will discuss on later. For these 4 type of connections, the transistor consists of 2 PN junctions, the emitter base junction and the collector base junction. So there are 2 junctions, PN junction, emitter base junction, always remember, and collector base junction, right? Similarly, we have maybe we will further see so many configurations, common collector, common base and common emitter. So there will be junctions, and 2 junctions will be there, emitter base junction and collector base junction, right? Now coming to the next point, now coming to the emitter transistor construction. So emitter is the portion on one side of transistor that supplies charge. Emitter means one who emits the charge carriers, right? So if my emitter is providing some charge carriers, suppose my emitter is N type, so it will provide number of electrons, charge carriers, to my collector and base junction, right? Similarly, so since this emitter needs to be heavily doped, as well as we have put width larger than the 2 regions, by the base region, by the collector region. So emitter is heavily doped region. This is the first point. And the portion on one side of transistor, if it is N type, then it will provide charge carriers, that is electrons, and otherwise it will, if it is a P type, then it will provide holes as charge carriers. Emitter of PNP transistor supplies whole charges to its junction with the base. Similarly, the emitter of NPN transistor supplies free electrons to its junction with the base. So this point is clear, That means if I have three portions, see, it is very simple to understand that this is my emitter and this is my base. See, this width is quite larger. Let me do this. What we do is, this is my emitter, this is my base, and this is my collector, right? So emitter, if it is n type, let's say, there are number of electrons but few holes, okay. So it will provide electrons, and these electrons can cross the junction also, but this needs to be emit the charge carriers, right? Now coming to the collector. Collector is the portion on the other side of the transistor, the opposite to the emitter. That means emitter, base, and then collector. So it collects the charge carriers provided by the emitter region. Whatever charge carriers, may be holes, may be electrons which are coming, it will collect the charge carriers. The doping level of the collector is in between the heavily doping of emitter and lightly doping of the base. So the collector doping level is between the emitter and base. That means it is lightly doped in comparison to the emitter region, right? So the doping level of collector is less than the emitter region but greater than the base region. So this point should be clear, and it should be important also. Similarly, if I talk of the width of these three regions, then the emitter width is highest, then collector width, and then the least is for the base region. The middle portion, now coming to the base, the middle portion is the base, which is forming two p-n junction. The base of the transistor is thin as compared to the emitter and is a lightly doped portion, right? So it is the lightly doped portion, that is the mid region, maybe p, maybe n. Okay, the function of the base is to control the flow of charge carriers. That means emitter is emitting the charge carriers, collector is collecting the charge carriers, and base is controlling the flow of charge carriers from emitter to collector. So these are the transistor construction points. Now coming to the BJT modes of operation. As I said, there are four combinations in which we can bias our emitter based junction and collector based junction. So out of these four, there are different modes, four modes also. For four modes of operation, the four types of biasing has been done. Like if I talk of cutoff region, cutoff mode, so that means I need to make it reverse, and if I want to transistor to act in the active mode, it should be forward reverse, and if I want my transistor to act in the saturation mode, then I will bias my transistor in forward biasing. That means, see what I have emitter based junction and I have collector based junction. So if I bias it in forward reverse, then mode will be active. Understood, right? If I bias it in forward, then the mode will be saturation. If I bias it in reverse, then it should be in cutoff mode. The transistor should work in cutoff mode, and if I make it reverse forward, then it is known as inverted mode. So these are the points. So forward reverse, forward forward, reverse reverse, and reverse forward. So there are two junctions in the bipolar junction transistor. Each junction can be forward or reverse biased independently, and thus there are four modes existing, in which the inverted mode is of least use, and it is not be used in the transistor operation. So here main modes of operations are active, saturation, and cutoff. Now coming to the forward active. Forward active is emitter base junction is forward biased and collector base junction is reverse biased, as simple as that. The BJT can be used as amplifier. The application of the active mode, what it has been said is, so in active mode the transistor functions as amplifier, right? As it is written, the BJT can be used as an amplifier in analog circuit if I make my emitter base junction forward bias and collector base junction in reverse bias. So the BJT will be used as amplifier. Now next, the cutoff mode. When both junctions are reverse biased, the transistor is acting in the cutoff mode. In this situation, nearly zero current is flowing. So the transistor is behaving like it is as open switch. So the cutoff mode is transistor, you can assume as open switch, no current is flowing, nothing. So both the junctions are reverse biased and there will be no current at all. Maybe some due to some minority carrier, maybe very less negligible amount of current may be there due to the flow of few charge carriers, very few charge carriers, but that will be nearly zero current. So transistor, we say that it is behaving just like as an open switch. Now coming to the saturation. Saturation region is that region where emitter base junction and collector base junction both are the forward biasing mode. So in forward biasing, both junctions are forward biased and the transistor will behave as a closed switch. So coming to this point, in saturation, the transistor functions as a closed switch, and in cutoff the transistor functions as an open switch. So this particular mode has not been used practically, but I have written just to show the combinations of these modes, right? So there are basically three important BJT modes of operation: active, cutoff, and saturation. Now here active mode operation, how the transistor is working in active mode. Active mode is which mode? Where the emitter base junction is forward bias and collector base junction is reverse bias. Now, so let us see. Here we have made this emitter, this is my emitter base junction. So this emitter base junction, we have taken PNP transistor. So this P terminal is connected to the positive and this N is connected to the negative terminal of the battery. So it is forward bias. So if it is forward bias, then positive holes will distract from the emitter and they will start flowing in this way, right? And they will start flowing to the collector portion. So here what they will do is they will just cross the base and they will go towards the collector. And here what is going to happen? But whereas the reverse bias junction of PNP transistor, this is negative. So negative will go away from the negative terminal of the battery. That means electrons present in the P region, they will move like this. So but they are minority in terms of P type is concerned. The electrons are in minority, so some minority current will flow, and here due to forward bias these majority carriers will flow. So the total current will be the sum of the flow of majority carriers towards the collector and the minority carriers towards the emitter. But since minority and majority current will both the currents are existing and they will sum to make the total emitter current. So forward bias junction of the PNP transistor, reverse bias junction of the PNP transistor has been shown. Now as I said, the most of the current will be due to the majority carriers, and these majority carriers are present in the emitter region, and these emitter region carriers will flow towards the collector, and the collector will collect this charge carrier. So majority current will be from flow, and this has been shown by this arrow. This is the current. The holes are moving towards the collector. This is the majority carrier current. Now some minority also, minority carriers, the minority carriers present in this P will distract from the terminal and they will start flowing like this, and the current will be opposite to the direction of the flow of the electrons. So current has been shown, but it is very less in comparison to the the majority carrier. This minority carrier current is very less. So here the depletion region widths are also being shown, here since this is a forward bias region, so the depletion width is very less, and since this is a reverse bias junction, so depletion width is very large. So we can explain this also. So the total current which is flowing from emitter to collector, this is the sum of the majority I total will be the sum of I majority carriers plus I minority. Okay, so both the currents are flowing. Now coming to the currents in the transistor. So this is very important, that now how to represent this all current in the mathematical formulation. So emitter current has been assumed as IE, and collector current has been assumed as IC, and base current has been assumed as IB. Now see the direction of the current first, then we will understand how this formulae have been derived. So coming to this point, so now this is my forward bias region, this is my positive terminal of battery. So current will start flowing like this. Current always flow from the positive terminal of the battery, so the emitter current will be the direction of the emitter current will be inside this. If I take this P and P, okay. Now since this particular region have collector base junction has been reversed bias, so the current will come to the negative terminal of the battery. So this current direction will be like this. Now the total charge carriers from emitter are making the majority current, and the total current is flowing from the emitter. So I can write IE is equal to IC plus IB, and this particular formula you need to learn always that emitter current is the sum of collector current and the base current. So emitter current is equal to collector current plus base current. This is a big formula and which is applicable to all the configurations, whether it is PNP, NPN, common base, common emitter, common collector. So you need to learn this IE is equal to IC plus IB. Now, so since IC is equal to IE is equal to IC plus IB, so this is my point of KCL. So IB should be downwards so that it can be added with the IB to make IE. Okay. So IE is equal to IB plus IC. In this way, we can write the formula. Okay. So by this type, we can define the direction of the currents. Now again, one more very important formula which we need to learn for all the configurations, the collector current. Again, that was the formula for emitter current, IE is equal to IC plus IB, that you will learn. I am telling so many times that you need to learn, because these particular formula you need to learn always, and these are applicable for all the configurations, so it is important. Again, the next formula which is very important, that is the total collector current. So the total collector current is IC majority plus ICO minority. This is also important, that the collector current is the sum of majority carrier current and the minority carrier current, right? So the minority current is called the leakage current and is given by the symbol ICO. So understand, this ICO becomes ICBO for common base configuration, and this same ICO becomes ICEO for the common emitter configuration. So for common base it should be ICBO, and for common emitter it should be ICEO. So I have IC is equal to IC majority plus ICO minority. So the minority current, where minority current is also called or known as leakage current. It is known as the leakage current, right? And this leakage current is defined as the IC current with emitter terminal open. The ICO is that current, if I open the emitter terminal, then the current will be called as ICO. Another important point at this particular stage, we need to consider that we have decided the direction of current in for the PNP. Let's say if it was in PN, then what was the current direction? For active mode operation, I will make it forward, and this I will make it reverse. Okay. Since emitter current is flowing into the negative terminal of the battery, so this should be I direction of IE, and here this should be the current is outside the positive terminal of the battery, then it should be IC, and to satisfy this, the IB base current from this KCL point, this is my KCL point. So here I can write IE is equal to IC plus IB. Okay, this is one also important point, that IC plus IB is equal to IE. So if it is NPN transistor, then also we can take the direction of the current in this way. Now coming to the common base configuration, the first configuration which we are going to discuss, that is common base configuration. So in the common base configuration, what we have done, we have provided the emitter, base and collector, and this base terminal has been grounded. the emitter terminal has been given the VEE supply, and the collector has been given the VCC supply, and the emitter base junction has been forward biased and the collector base junction has been reversed biased. So the base is common to both emitter and collector, then it can be said as the common base configuration. So for common base configuration, one thing which we should consider, that common base, for common base or common collector or common emitter, there is a key point for understanding all the configurations, that let's say emitter can be given input and output both. Always remember, the collector can be the output can be only taken from the collector terminal, and the emitter, as far as my base is concerned, only I can give input to my base. So base, input, collector, output, emitter, both input and output. So this is the key point, how we can decide which configuration is given in the numerical or which configuration has been asked about when we are searching the mode or configuration of the transistor, right? So here the common base, let's say what I have told, that the base can be given only input, the collector can only output can be taken, but emitter input and output both. Okay, so this is the key point, this you need to always remember for searching the mode of the configuration in which your BJT is working. Okay, thank you for, that's all for this particular lecture. We can discuss other configuration in next video.